Today's lab is going to be about current sources. Current sources are very important to integrated circuits. They're found everywhere, analog integrated circuits. So it's important that we understand how they work. So the first part of this pre-lab is to determine the output resistance of a simple current source. So if I draw real quick here. VSS. We want to know the output resistance of that circuit. So we start with the small signal model. I'll call this guy M1 and M2. And I usually start drawing these from the output and go back to the input. There's not really an input here, but I'll start from the output. So from the output we see M2, which has the resistance RO2, and in parallel with that we got the current source GM2, VGS2. Those two go together, and gate voltage, this is the source, which is grounded. VSS is small signal ground. Got plus or minus VGS2. And over on the other side, we have a diode connected transistor, which in the small signal model can just be replaced with a resistor of 1 over GM1. And in parallel with that, we have our ref. And both of those go to ground because VDD in this case is also small signal ground. So RF goes from the gate to VDD, which is ground, so that's why it's the ground here. And 1 over GM is just the resistance from the gate drain connection to the source, which is at VSS, which is ground. And so VGS1 is equal to VGS2 in this case. But you'll notice that you just have a couple resistors here. There's no voltage or current components. It's just two resistors connecting this ground node to nothing else. So that really tells you that this is also going to be 0 volts here. And so VGS1 equal to VGS2, that's small signal ground. So that means this component, GM2 VGS2, is going to equal 0. And basically all you're left with is just RO2 in this circuit. So you could say this equals just a resistor, RO2. And so R out is just equal to RO2 in this case. So pretty simple. The Wilson is much more difficult, so I'm not going to go into that here. You actually have to do some nodal or mesh analysis of the small signal model in order to derive those equations. But I will write down the equation here for the Wilson, just to talk about it for a second. And this is given in the lab handout. GMRO over RF plus 1 over RF. So what's important to note here is that there's dependence on the reference resistor value and the output resistance. Now the lab says this is approximately equal to GM RO squared, which is what you learn in class, but that assumes that RF is very large. In the event that it's not very large, like it will be in our lab, then you have to use this bigger equation in order to estimate what the output resistance is, because GM RO squared will overestimate what the output resistance will be. So that's an important note. This will give you possibly 10x larger than what you'll actually get. Okay, the next part of the pre-lab is to determine what the reference resistor values need to be in order to get 4 milliamps of current. And they give you all the MOSFET design parameters, so you just have to figure out the resistance from there. One thing to note about diode connected transistors, if you remember from lab 2, is they're always in saturation. So you don't have to deal with the triode linear equations of the transistor, you just need the saturation equation. So this was part 1. Part 2, going to use that same circuit for the simple, and we'll just consider, let me redraw it. VDD. This isn't ground actually, this is VSS. This is our ref. And we don't know what the gate voltage is. We'll just call it VG. Okay, we don't need to worry about M2 because it's just going to mirror the output. So we just need to figure out what VG is in order to get 4 milliamps. And once you know what VG is, you can calculate RF using Ohm's law. So pretty simple. So let's start with the transistor. ID is equal to 1/2 K prime Kn prime W over L VGS minus VT squared. Also remember that VGS is equal to VG minus VS. And if you look at this equation, you know everything in it except for the gate voltage. ID they tell you is 4 milliamps. Kn prime WL is given to you. VT is given to you. The source voltage is -5. But realize that this is a negative sign here, so it'll end up being a +5. But VS is equal to VSS, which equals -5 volts. So if you plug in all of that, you can solve for VG is equal to something. And I'll let you solve it. Once you know the gate voltage, you can figure out our ref by Ohm's law. VDD minus VG equal to 4 milliamps times RF. And you can solve that for RF, because you'll know the gate voltage, VDD, is +5 volts, and the 4 milliamp current. Okay. Just looking at the lab really quick. Right. So the next is to figure out the same for the Wilson. So let's draw that circuit. And this one's a little trickier. got some stacked NMOS transistors. And this one goes this way. This one goes this way. VDD, VSS, and the lab I'm looking at says that VDD and VSS are 10 and minus 10. We're going to change that this semester to 5 and negative 5 because the analog discovery module can't do plus or minus 10 volts. So we'll use 5 volts for this class. And let me number these correctly. M1, M2, M3, and M4. So this one's a little trickier, but it's basically the same idea. In order to figure out the reference resistor, they tell you the current needs to be 4 milliamps. We can do Ohm's law again once we figure out what that voltage is at that node. And a little observation, you'll notice that it needs to be 2 VGS values above VSS. So VSS, you have to go up VGS here, call it VGS1 to get to this node, and then if you were to go up VGS2 here, then that would get you to this node. I'll just call it V1, I guess, no particular reason. So V1 is equal to VSS plus VGS1 plus VGS2. So that's not too bad. We know VSS is minus 5 volts. VGS1 is the same as what we solved in the previous part. When you did this equation, you solve for VG. We can replace that with minus VS, where VS is equal to VSS, so minus 5 volts. And I think this comes out to around 2.5 volts total if you did this right, just for reference. Now, at a quick glance, you might think VGS2 is equal to VGS1. It has the same current. The inputs to this equation are the same, so why wouldn't it have the same VGS as the bottom transistors? But you have to remember body effect. Body effect changes the threshold voltage. So actually all the input parameters are not the same. Threshold voltage is different for M2 and M4 in this circuit. So we don't know what VGS2 is. But first we need to figure out what the threshold voltage of M2 is, then we can use that saturation equation again and figure out what the gate voltage is and VGS voltage. So threshold voltage equation, VT is equal to VTO plus gamma square root 2 phi plus VSB minus square root 2 phi. Gamma is 0.9 volts to the 1/2. I think that's given to you. 2 phi is 0.6 volts. 0.6 volts. VTO is 0.7 volts. VSB is the only tricky variable here. So that's the source voltage minus the body voltage. Minus VB. The source voltage is equal to the gate of M1 and M2. And we figured that out earlier in the simple circuit. We figured out what VG was in that scenario. So VS is equal to VG. VG1, which you figured out earlier. The body is equal to VSS. All the NMOS body you can consider connected to the lowest potential, VSS. Minus VSS here, where VSS is, again, minus 5 volts. So just watch your negative signs. So yeah, you can use this to solve for VT be 1 and 3. Oh no, not 1 and 3. 2 and 4. The stacked transistors. VT 2 and 4. Once you have the threshold voltage, you can calculate what VGS is. So go back to saturation equation. ID is equal to 1/2 Kn prime W over L. VGS 2, 4 minus VT 2, 4. And you can solve that for VGS 2, 4. Because you'll know the threshold voltage now, the other parameters are the same as what you've been using. And ID is 4 milliamps still. So once you have that, you can plug that on up here to figure out what V1 is. Once you know V1, it's just Ohm's law again to figure out RRef. So VDD minus V1 is equal to 4 milliamps times RRef. And solve for RRef. And just remember that VDD is 5 volts in this case. I'll change the lab manual to say that correctly. Right now it says 10. Alright, there's one more calculation we have to do. And that is to figure out the maximum load. And the maximum load will drive the output transistors into triode, which is not where we want them to be if you want it to have high output resistance. So let's start with a simple source. We'll just draw the output here. This guy has VG1 on the gate, RL to VDD. Keep drawing that as ground. It's VSS minus 5 volts. So in order to stay in saturation, VDS has to be greater than VDS sat, which is VGS minus VT. I told you earlier that VGS should be around 2.5 volts. If you did the calculation correctly, VT is 0.7. So that should be VDS has to be greater than 1.8 volts in order for this guy to work. So we have to use Ohm's law again. This is VDS. We know what the requirement is. We need at least a minimum amount of 1.8 volts across it. And so doing Ohm's law, VDD minus this voltage here, which would be VSS plus VDS. Really, this is VDS min, the minimum amount, is equal to 4 milliamps times RO. VSS is minus 5 volts. VDS min is 1.8 volts. And so you can solve for RL from there. So that's not too bad. We have to do the same thing for the Wilson. Wilson's a little bit different again, so just draw it real quick. This was M1 and M2. And we called this node V1 before. And again, I'm used to putting ground there. That's VSS. I forget what we call this. This would be VSS plus VGS1 at that node. So let me check the notebook up. Okay, so similar process here. We need to figure out what the minimum voltage can be at this node before we go into triode somewhere below it. So again, this guy's diode connected, so he's sitting at VGS1 across its terminals. So that's why this node is VSS plus VGS1. And then again, there's a minimum VDS requirement on M2 based on that same equation. But the difference here is VT isn't 0.7. It's what we calculated earlier in part 2. So VDS of 2 has got to be greater than VGS 2 minus VT 2. And you figured out these quantities in the previous part. So you can solve that. It's going to be greater than 1.8 volts this time. Actually, I lied. I think it's going to be exactly 1.8 volts again, because VGS and VT will track each other. So yeah, I think that's going to be 1.8 volts, but just double check that. So once you know what VDS2 is, you can calculate RL again using Ohm's law. So VDD minus this voltage here, which is VSS, plus VGS1 plus VDS2 equal to 4 milliamps times RL. And that will give you RL equal to some value. And that's the maximum load that you can handle before M2 will go into triode, because this node will drop too low. That's it for the Prelab. Just have to do the simulations now to prove this theory is correct.